Hello, everyone, and welcome to today's webinar. My name is Chris Nova, Marketing Operations Coordinator at Thermoanalytics and host of today's webinar. Our presenters today are Vishnu Ranganathan and Dr. John Bate. Vishnu is a field application engineer with more than 3 years experience in battery thermal management and fuel cell simulations. He received his master's degree in computational sciences and engineering from Technical University Braunschweig, Germany in 2018, and has been a member of the Thermoanalytics family since 2021. Dr. John Bate is industry director at Modelon Inc. with over 20 years experience with Modelica. He has worked across different engineering domains with a specialty in thermofluid systems. Dr. Bate was the first employee of Modelon Inc. in 2012 and has worked in a variety of roles to establish Modelon as a leading provider of system simulation solutions in the US. Dr. Bate received his bachelor's in mechanical engineering from Georgia Institute of Technology in 1995 and PhD in mechanical engineering from the University of Michigan in 2000. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Vishnu, if you're ready, you may begin.
Yeah, thanks, Chris. Welcome everyone for today's webinar on the topic an approach to controller design using a coupled 1D 3D EV model. So today's webinar will be a joint webinar with Modelon, and John is also here with me. So on today's agenda will be as follows. I will give the brief introduction of our company and the objective of this study, and then go through the setup of this three-way coupling process. And John will explain the 1D system model in the Modelon. And later I will jump into explaining the CFD and thermal model for battery and cabin. And followed by, we'll discuss the results for cabin cooling only, followed by cabin and battery cooling, and the HVAC energy consumption for these two cases. And we will discuss the conclusions of this study and other strategies given by Thermoanalytics, and also the next steps of the process. So Thermoanalytics is a CAE company offering a wide array of engineering solutions throughout many industries such as automotive, aerospace, and electronics. We are leader in thermal solutions, especially heat management solutions for transportation industry. Thermoanalytics started out of Michigan Technological University, developing thermal software for Ford and the US Army. Today, our software is distributed throughout the world with offices across US and Europe. We also have several distributors in Asia, including China, India, Japan, and South Korea. So TAITherm is our 3D thermal solver, which solves for all modes of heat transfer. We also have an array of modeling extensions for various applications like battery, exhaust, drive cycle, and human comfort. CoTherm is our co-simulation and automation coupling software. It facilitates the coupling between TAITherm, CFD solvers like Star CCM+, ANSYS, OpenFOAM, etc., and other 1D tools like GT, Modelon, AIMSIM, MATLAB. In this presentation, we'll be looking at the coupling between TAITherm, battery extension, and human comfort, and OpenFOAM as a 3D CFD tool, and 1D system tool as a FMU from Modelon for a cabin thermal modeling application. Battery extension contains an equivalent circuit model for batteries where the heat generated is based on characteristics of a cell and given boundary condition. For human comfort, we are using our thermophysiological model, and to assess comfort and sensation, we are using the UC Berkeley models. So I will hand over to John to introduce the Modelon.
Thanks, Vishnu. From the Modelon side, we're a system simulation software and services company. We were founded in Sweden in 2004. We work like Thermoanalytics across many different industries: aerospace, automotive, energy and process, and HVAC and our primary ones. And you can see a couple of customer references there. From the Modelon side, we deliver both products and services with the goals to help our customers develop and apply open standard modeling and simulation processes to accelerate design and verification. We operate primarily with two open standards, Modelica and FMI, Functional Mockup Interface. We'll describe those uses a little bit further in the presentation. We're distributed around the world. We have roughly 100 employees in Germany, Sweden, India, Japan, and in the US, where we are in Ann Arbor, Michigan, and in Hartford, Connecticut. Go to the next slide. So today we'll be talking about our vehicle thermal management 1D solutions that consists of a number of different libraries that we will apply as part of the model that we'll show you later. That's air conditioning library, heat exchanger library, liquid cooling library, and also electrification library, which is our library for 1D battery simulations. Our models are available on multiple modeling and simulation platforms, including Modelon Impact, which is our newest and our own platform. That's a cloud native 1D system simulation tool for building and simulating models. So what are the key challenges that we're addressing today? Obviously, for EVs, energy management and vehicle range are coupled and are a huge challenge. How to best use the energy available. In addition, HVAC systems are being used not just for passenger comfort, but are also key parts of the powertrain because they are typically cooling key components like batteries and motors and other parts of the EV powertrain. So the combination of the physical system design and also the controls need to manage and optimize both comfort and energy efficiency. What you see on the graph is sort of a typical challenge that we see with EV systems that manage both passenger comfort and battery cooling. So the curve in red shows the cool down of the cabin, starting from a very, very hot soak temperature and then turning on and cooling down. And then the curve in blue that you see starts off at the same trajectory as the red curve, but then the battery requires cooling at a particular time, and you can see how that degrades the cabin comfort because the cooling is now split between both the battery and the passenger. And then once the battery doesn't require cooling, then you can accelerate cabin comfort. So managing this trade-off is something that's extremely important for hitting attribute targets, and this is part of what we'll discuss today, along with the energy consumption.
Okay, thanks, John. So now let's look at the setup of the three-way coupling. So the main objective of this study is to predict the energy required by an EV to cool cabin and battery from a hot soak scenario where the car is parked for about 7 hours under the sun. So in this case, we will have battery temperature as high as 45 degrees C, like you see on the small graph, and also the cabin air temperature will be also close to 60 degrees C. So we need to cool both the cabin and the battery simultaneously. So we could think of this whole model and can be categorized into three main sub-models, like on the left, the 1D system model, and on the top, the 3D battery thermal model, and then we also have the 3D cabin thermal and the CFD model. So in here, the co-therm acts as a master in initiating and controlling the communication between various CAE tools during the coupling process. The 1D system model accepts a bunch of inputs, variables like max battery temperature, cabin air temperature from CFD, and it also outputs battery coolant mass flow rate and temperature back to the 3D thermal model, and also the vent inlet temperature back to the 3D CFD model via co-therm. And one more advancement which we will look later in the presentation is to control cabin vent inlet temperature based on the human based on the human sensation and comfort inside the cabin. So with this advanced controller, the power required to cool the cabin can be significantly reduced. And by using this sophisticated 3-tool coupling process, the energy required to cool the cabin and the battery can be evaluated and also optimized, so which will in turn increase the range of the EV. So this slide explains the coupling information of transient run between the 3 tools, TAITherm, OpenFOAM, and 1D system as a FMU. On the right, we see the COTherm canvas, which acts as a master, like I said before, to interact between the 3 tools. And here you see how the different process operations are connected together, and the data can be also monitored during the run. And further, the COTherm also supports Python and shell scripting. So here the cooldown process is for 30 minutes. And initially for the first 15 seconds, the FMU, OpenFOAM, and the TAITherm model are coupled with 5 seconds coupling interval by running the OpenFOAM like with a full-blown solver, meaning you have the momentum and energy solver to obtain a fully developed velocity field inside the cabin. And afterwards, OpenFOAM is run with a frozen solver, meaning the momentum solvers are frozen, and we only solve transiently for thermal side. So this will increase the turnaround time, like you see here. By running the fully blown solver, we run like 2 days on 48 processes, and then later on we just run for 15 hours for the rest of the cooldown process. And at each coupling interval, the data are exchanged between the 3 tools, the FMU, OpenFOAM, and TAITherm. And at each coupling step, the simultaneous calculations of various variables, like we discussed in the previous slide, are exchanged. And so the next slide will be the setup of the 1D model, and John will talk about this.
Thanks, Vishnu. So here's the 1D model. So what you see on the right-hand side is our starting point. This is actually a fully executable simulation model on the 1D side, including the refrigerant loop, the battery coolant loop, a simple air distribution system, and a lumped cabin, and also our 1D system model of the 1D model of the battery. So this is the starting point for our model. And what you see on the left-hand side exploded is the refrigerant loop. So we'll discuss this. This is a 1D model of the refrigerant system, including all of the components. So in this case, we're doing a parallel loop. So it's a compressor followed by a air condenser, and then split paths. One path is for the front evaporator. That's where we get our cabin cooling. And then the second path is the battery chiller. This is where the cooling for the battery will come from. And here you can see a single compressor system needs to deliver refrigerant that will be split between the 2 paths. And this is where we get different amounts of cooling depending on how we control the system for both the cabin and the battery. Obviously, the capacity is limited by the size of the components. So this is the starting point for the model that we'll deliver to TAITherm. So if we go to the next slide, this shows the model as it's integrated with TAITherm. What you can see are a couple of cuts in spots where we interface with TAITherm. One cut is at the bottom of the screen that shows the interactions between the coolant system part of our model, and then where we get information coming back from TAITherm, which is the battery temperature and the return coolant as it exits the battery. That's handled on the TAITherm side. On the upper left, you'll see the control inputs. So we'll be talking about controls a little bit more in this seminar. So we typically do model the controls on the 1D side. And the controller that you see here is basically the subsystem controller for the refrigerant system. So it takes target conditions like evaporator air out, battery temperature targets, and then determines how to run compressor and also how to set the valve superheat targets for the refrigerant system. The other cut that we make with the system is on the air side. So we cut out our cabin and we take air inputs from the 3D model. So that's the cabin temperature is predicted from 3D, and also the pressure potentially and the humidity in the cabin. What this model outputs for the 3D side is shown on the right-hand side. That's the air duct discharge conditions that we predict from the 1D system side. Flow rates, temperatures, humidity, various outputs from the refrigerant system for post-processing and tracking. So things like the powers of the evaporator, the chiller, the compressor power. And then we also output the coolant conditions to the battery. That's the coolant flow rate and the coolant temperature. And those are output to the 3D side and then run there and then return back to us as the outputs from the battery. And as Vishnu mentioned, this is all done by creating what's called an FMU, a functional mockup unit. We should describe what that is a little bit. So FMI is the standard. It's called Functional Mockup Interface, and it's a standard for exchanging models between different modeling and simulation tools. So any model that's exported from an FMI compliant tool is called an FMU, a functional mockup unit. It's basically a self-contained model that can be coupled with another tool. It often includes an executable, the solver, everything required to run. So this is a standard interface. If you're interested, you can go to the FMI website and you can see a list. There's probably over 150 tools, the functional mockup interface. So it's a very nice way to couple tools together, and one that we use very regularly with our 1D system models.
Okay, thanks, John. So let's look at now the setup for the TAITherm side and later on also on the CFD. So here I have a typical EV car. So with some of the seats and roof and dashboards all are as modeled as a multi-layer, and it's pretty easy to model the multi-layer in TAITherm by selecting as many layers, and each layer can have a different thickness and different materials as shown here. And this slide shows the problem setup. So here I have a scenario, like a work scenario in Phoenix, Arizona. For example, an employee drives to work, parks his car in a parking lot where it sits and heats up in the sun for about 7 hours. And in the evening, our employee heads out for a drive to home and he runs his AC on the max speed. So here on the animation, you see during the 7 hours hot soak how the temperatures inside the car is increasing because of the movement of the sun. For example, on the seat and on the dashboard, as marked here, goes up to like 90 degrees, and also the seat also goes up to 60 degrees, and then later as the sun moves the temperature drops. And as a notice here, the human or the employee is preconditioned in the office environment, and later he enters inside the car of the hot car. So the setup of the cabin in the CFD side is shown here, where we have about 2.5 million cells, and you see how the mesh is resolved around the human and the seats. We have a minimum size of 5 and base size of 10 millimeter. The mesh is done with SnappyHex mesh of the OpenFOAM. And on the boundary conditions, so we have like 4 inlets on the front dash and then 2 inlets on the rear, and each inlet has a specified mass flow rate and also the temperature, which comes from our 1D tool. And then, like I said, first we solve like a fully blown solver with buoyant pimple foam, and later just by freezing the momentum using thermofoam, and transient duration is 30 minutes. So now let's look at the battery modeling in TAITherm. So here the battery pack of a typical EV with a prismatic cells is shown. So here we have a battery pack of 8 modules, and in each module we have 24 prismatic cells, and the configuration is 2 in parallel and 12 in series, and all modules are in series. And we have total of 192 cells, and each cell has a capacity of 117 amp hour, which corresponds to a total capacity of 82 kilowatt hour. And on the top you see how the cold plate cooling channels are modeled along with the battery pack, and the heat generated in the cells is based on this drive cycle. So based on this current input, the heat is generated in the batteries, and that is required to be cooled. So the setup of the cooling channels. So we have inlet and outlet, and the inlet we have a specified mass flow, and the specified coolant inlet is from the 1D system. And also the outlet of the coolant goes again back to the 1D system to control the coolant in temperature, and the heat generated from the cells, those temperatures are mapped from TAITherm to the CFD. So let's discuss the results now. So initially we discussed the cabin cooling only, so which means the battery cooling is not included in these results, and the results are categorized into 3 main topics. So one, we start with the cabin cooling without the controller, and the second we look the cabin cooling with a bulk temperature controller, and then finally we look the cabin cooling with human sensation comfort based controller. So results for without controller. So this plot is a velocity plot inside the cabin, showing how the air from the vent inlets are distributed, and clearly we see that the impingement of air, the cold air, is on the driver's neck, face, and also on the left hand. So here are the results for the cabin cooling only without the controller. So on the left, I plotted the cabin air temperature over 30 minutes of the cool down. So initially the cabin starts really hot, about 58 degrees Celsius, and it cools much faster and reaches about 16 degrees C in 30 minutes. And in the middle we have the vent inlet temperature, so which is the temperature given as a boundary condition to the CFD. And here we set the target to 10 degrees C, and then we clearly see that the target is reached around 7 minutes, and it stays constant there since we don't have any controller, and this results in the further decrease of the cabin air temperature. From 7 minutes, you see it's still decreasing. And on the right we have the corresponding compressor power for this scenario of cooling. So here I have the animation of the mapped fluid temperature from CFD to the TAITherm model. Here the fluid temperature, as you can see, gets colder and colder during the 30 minutes cool down. We also see the impingement on the left hand of the driver as well as on the face. And here you see that the fluid temperature goes below 15 degrees at about 30 minutes. And on the right hand, I have plots of sensation and comfort for the face and left hand segment of the driver. So here the sensation means perception of hot or cold, and that is measured on a 9-point scale from -4 to +4, +4 being very hot and -4 being very cold. Similarly for the comfort, +4 being very comfortable and -4 being very uncomfortable. So initially as the driver enters the car, so he's feeling very hot and very uncomfortable. And as we cool down the cabin, the temperature drops and as you can see, the sensation drops as well, and the comfort increases. But this increase in comfort changes its direction and goes to fall again. It's because we cool the cabin further, so which reduces the comfort of the humans. For example, the face as well as in the left hand also drops pretty fast. So when we look at the overall comfort and sensation, so this is an aggregate measurement of all body parts of the driver. So this plot also shows the similar trend like the face and left hand. So we start from very hot and very uncomfortable, and then as sensation drops, the comfort increases. But as the sensation drops further and further, the comfort still remains on the negative side. So which is still not good for the human. So then we came up with a bulk temperature controller, meaning you just have one temperature representing the whole cabin. Like we could take the average of the whole cabin volume and give that temperature to the 1D system model. And we would like to have this bulk temperature around 23 degrees Celsius. So this kind of temperature keeps the human in a neutral state. And then the 1D system model will have a controller or adjust the vent inlet temperature on the CFD side. So similarly, I have the three plots. So the cabin air temperature, so which starts very hot, and then here I have marked the 23 degrees Celsius for the reference. Here you see the 23 degrees C is reached in 13 minutes, and it gets maintained around that temperature. So that is because when you look at the vent inlet temperature, so we have set the target of 10. So the 10 is reached also similarly like 7 minutes, and it is maintained for a while, and later as the cabin temperature drops below 23, the vent inlet temperature tries to adjust, so it is increasing, and then the cabin temperature is so maintained around the 23 degrees C. So on the right, we have like the compressor power for maintaining this scenario with the controller. And when we look at the mapped fluid temperatures, now we see that the cabin is not cooling much as we saw in without controller. So this is the fluid temperature is very close to 23 degrees C on you see on the human as well as on the rear seats. So similarly, the face and left hand comfort, it starts like +4 sensation, -4 comfort, and the comfort increases. And also here we see that the sensation is dropping a little bit, and then it's also increasing after 12 minutes or so. And then the comfort also has an effect here, which also increases. For the face, it's still on the negative side, but on the left hand, you see it is increasing to the positive side of the comfort, but also at the later stage, it drops. So when we look at the overall comfort for all the segments, also shows a similar trend. You have the gain. So when you increase the sensation after 12 minutes, you see the comfort increases, but it still lies on the negative side. You don't see that the driver is comfortable. He's not comfortable yet. So this is because we have the bulk temperature controller, and meaning we over predict for the controller to cool the cabin. So here I have plotted two temperatures, so one being the bulk temperature, which we discussed, and the one being the breathe temperature of the human. So the temperature sample very close to the human breathe, like shown here, so which is the blue color. And here you see like at the 5 minutes, the difference between these two plots is like 10 degrees C. So we are over predicting to cool the cabin, and which in turn results in a much worse comfort for the driver, as we are not looking at the temperature localized, meaning we are not looking the temperature close to the human, and to maintain the comfort of the human. So this in turn results in a controller with the sensation and comfort based. So the main idea here is we feed back the driver sensation and comfort back to the 1D system, and the 1D system will now try to set the event inlet temperature. So in this way, we are localizing the comfort very much concentrated on the driver front and not concentrated for the overall cabin. So the main idea of the controller is shown in this flowchart. So basically, you get the sensation and comfort from your TAITherm, and you have a supervisory controller, which is in OpenFOAM, will ask the Modelon to set the evaporator air temperature, and in turn, the 1D system will set the compressor speed, evaporator, and chiller positions, etc., so as to give vent inlet temperature based on the sensation. So here in this architecture, so we have the supervisory controller decoupled from the 1D system so as to not to regenerate the 1D FME. So similarly for this controller based on sensation and human, we also have these 3 plots, and I also have the 23 degrees C marked as a reference, and the cabin temperature starts to decrease and it reaches 23 degrees C in about close to 5-6 minutes, and then it is getting maintained around this temperature. And similarly for the vent inlet, still we have the target set to 10, and then later on it is increased based on the sensation of the human. And the compressor power for this scenario is also plotted on the right. And in the middle, as to note, you see even before the vent inlet temperature reaches its like the constant 10 degrees, so it is getting increased because of we already achieved the required sensation comfort, and then the controller jumps in to take to increase the temperature of the vent inlet. So similarly, the mapped fluid temperature is shown, and here you see the cabin is not cooling much, and the cabin is maintained around 23 degrees. The fluid temperature inside the cabin is maintained around 23. And this is reflected in the comfort and sensation plot of the face and the left hand. So here we start similarly, like very hot, very uncomfortable, and then about 5 minutes or so you reach the peak comfort, and later the sensation is not dropping further, and it is getting maintained, as well as the comfort is also on the positive side for both face and as well as on the left hand. So this reflects also in our overall comfort. So after about 12 minutes, or from the 10 minutes or so, we have the sensation maintained very close to the neutral state, and this shows that the comfort can also be improved and it's on the positive side, and this has the better comfort for the driver. So now we can compare some of the energy consumption for these cases. So in this case, I have compared the compressor power for cooling cabin only with the bulk temperature controller, and then with a sensation-based or comfort-based controller. And here we see, since on the bulk temperature controller, we are over predicting by looking at the bulk temperature of the cabin instead of localized temperature near the human. So here we see there is like 16.5% more power is needed to attain same kind of comfort. And in the following slide, I have plotted the two graphs, so one without the controller and one with the sensation-based controller. And by using the sensation-based controller, we see that the power consumption is reduced to 8.5%. And this shows that we can maintain the comfort of the human to a better state by using less power. So now let's look at the results, also including the battery. So meaning we have now both cabin and the battery. So here the controller is said to have attained the battery temperature of 30 degrees C. And with that, the controller will set the coolant inlet temperature. And here you see the heat is generated based on the above drive cycle, and the battery is cooled to the set target, so below 30 degrees. And also you see how the cabin is also cooled here. So in this plot, so we have the battery coolant, the maximum battery temperature in the middle, and the battery cooling power. So let's look at the middle plot. So the battery starts really hot, about 42 degrees C, and then it cools down to the set target of 30 degrees C in 28 minutes. And similarly, when we look at the coolant inlet temperature, it starts about 30 degrees, and then it slowly cools down as the compressor keeps working. And then when it reaches 28 minutes, you see the line is flattened, it is not cooling further. This is shown on the rightmost plot, the battery cooling power. You see it increases and stays almost like maximum power for a while, and when it reaches the target of 30 degrees C at 28 minutes, the cabin cooling power is like switched off. So now we compare the cabin air temperature for cooling cabin only, and on the right we have cooling cabin with as well as cooling the battery. So on the right we have a cooling cabin and the battery, and on the left we only look at cooling cabin only. So we start with a similar temperature of 58 degrees C in both cases, and then as also here I marked 23 degrees C as the reference temperature. So as the human feels about neutral state in this temperature. And at 5.5 minutes, we see that the cabin temperature is reached to 23 degrees C. And whereas by cooling cabin and the battery, we see that the cabin temperature is reached to 23 degrees C in about 10.5 minutes. So similarly, we also have the comfort plots for both cases. And on the left, we see the time to comfort is achieved much quicker than on the right. So by cooling cabin only, we reach the comfortable state in 4 minutes for the phase segment. And when we cool both cabin and the battery, the comfort of the phase is achieved at 7 minutes. So similarly for the left hand, we also see the similar gap, like 4 minutes for the left hand to reach its comfortable state, and 7.5 minutes. So when we look at the overall comfort as well, it also shows like 4 or 5 minutes difference between these two cases. So this is because the time required to cool the battery needs much more time than just cooling the cabin. So when we look at the compressor power, and we see that so the orange one shows when we cool both cabin and the battery, where you see that the compressor power still remains on the higher side. since the battery cooling requires much more power, and that's why you see a very big difference here. And when you just look at the cabin cooling only without battery, it is much lower. So this shows that cooling both cabin and the battery requires more power. So which in turn also reduces the EV range. So conclusions. So in this study, we demonstrated the hot soak scenario. We started with the hot soak scenario and we cooled down the cabin as well as the battery by using the 3 tool coupling using TAITherm, CFD, and 1D system tool from Modelon. And we also saw that with use of the controller, like the sensation and comfort based controller, the better comfort is achieved, as well as we also save energy by 8.5%. And result also showed that during the hot soak scenario, when the battery is also like on the higher temperatures, so it requires also cooling, and this increases the significant amount of compressor power in this scenario. So thermoanalytics have also showed some of the other cabin controlling strategies based on different type of comfort we look into. So for example, the first one would be the break to mean value of the human. So there is a webinar already done by one of my colleagues. And also the other thing would be to have a reduced order modeling of the cabin by assessing few variables like mass flow rate from the vents, or also adjusting the vent positions and flow directions. So if you want to have a look at these, please feel free to look at on our website. So the next steps would be the following. So we could evaluate different HVAC sizings and HVAC architectures to analyze different interactions between the battery and cabin cooling performance, and also evaluate the energy consumption, and also how we can optimize and increase the EV range. So more on the first topic, John will say more on this in the next slide. And the next point would be also to concentrate on some of the body parts, like localized, like either on the face or hands, so as to reduce the energy. And also to evaluate different cooling plates for the batteries, and also some different cooling optimization study. We can also further decrease the power required to cool the battery. And last, we also can evaluate the lifetime of the battery based on the hot soak scenario. So every time when we start the battery really hot, and what would happen in the long run, so if we don't cool the battery much. So these are some of the topics we can discuss further as the next step. So yeah, John will explain the optimization on the HVAC.
Yeah, thanks, Vishnu. So for this work, we did one particular refrigerant system with the parallel architecture, but obviously there are many kinds of systems that we can bring to these applications. The system architecture is obviously a very important choice in these kind of applications. Are we doing a conventional system, or more commonly in EVs, a heat pump system? There's many different ways to achieve those kind of systems, not just sort of the parallel path, which is a very simple approach that we showed in the system that we integrated here, but you could do what's shown in the upper right, which is a all coolant based system that has parallel paths for coolant for both cabin cooling and battery cooling. There are also many different types of these systems where you determine where you want your fluid interactions to appear. Do you want it to be refrigerant coolant interactions, refrigerant air. So there in the bottom, you see a couple of different paths, including some with front and auxiliary evaporators if you need more cooling power. So, really part of this question includes what kind of architecture are we going to use? Are we going to use a single system or a dual system? There could be advantages of having separate systems potentially for cooling both cabin and battery, or combining them in clever ways. And obviously there's cost associated with parts that needs to be considered. And these are all things that we handle on the 1D side with our models. In addition, we can handle component sizing, right? Once we decide on an architecture, obviously we have to figure out what is the right size for the various components. Refrigerant system optimization. So what kind of refrigerant are we actually using? How would the system perform if we went to a different refrigerant is something that we also typically handle, as well as how to optimize charge for performance and minimization of compressor power. And we hinted at some applications here involving range, but on the 1D side, obviously we can run full drive cycle models, including the electrical part, the motor, the vehicle, so you can get a really nice closed loop answer on actual drive cycles of interest. And I think one of the really interesting combinations of the 1D, 3D approach is that we handle a lot of the design-oriented questions on the system model side in terms of the architecture and the component sizing. On the 3D side, you can also think about how you would optimize, say, the glazing, size of glass, vent locations, how the air is distributed inside the cabin. Those are definitely 3D type of questions that you would be able to answer with the TAITherm tool. So I think there's some really interesting synergies and nice ways of coupling these modeling methodologies together to get different kind of answers than you might get from just one approach by itself.
Yeah, thanks, John. So here are some of the references used for this study. Yeah, with that, I conclude the presentation, and we are open for the questions now.
All right, thanks, Vishnu. Thanks, John. So yeah, we'll open up for questions here. First one, is there any limitation on the choice of system simulation tool to model the controller?
Yeah.
You want me to handle that one?
Yeah, you can go ahead, John.
Okay. Yeah. So I would say in general, this approach is pretty flexible. So the integration with TAITherm was done with an FMU. So it's possible to bring to architecture systems with maybe even the controls completely separate from even the 1D side, and then you would couple the controls and the 1D side and the 3D side. I think in general, it's often handled on the 1D side because we have a pretty flexible modeling language to achieve that, but there are lots of specific controls type tools that are really great for controls. And I think you could use effectively anything here that could be imported as an FMU, and that opens up other tool couplings as well.
All right, thank you. A question about co-simulation speed. What is the speed ratio?
So I can take on this one. So the speed ratio, like I explained, so initially when we run this, the CFD is the bottleneck here. So when we run the full-blown CFD with the momentum and energy, it takes a lot of time. It's a transient simulation. So that's why we came up with this approach. Since we run the AC on the max cooling, we have the constant mass flow rate. So we have run the first few seconds to get the fully developed flow, and then later on we frozen the flow so that then we could run just the energy solver so as to fasten the computational time. So typically the turnaround time would be like initially to run the transient full blown like 2 days, and later on just overnight, so would be like 2.5 days, I would say.
Okay, thank you. Do we require the battery module and human comfort module of TAITherm for this study?
Yes, that's right. Yeah, we should require the both. Yeah.
All right. How to implement it in the real application? Is it not possible to do CFD simulation in the real driving condition?
Yes. So in the real vehicle, we should implement few of the sensors, like monitoring the temperature of the human at some body segments, for example, at the face or the hands. And then we could also monitor the temperature, air temperature inside the cabin as well at certain locations. And then we could build a reduced order modeling with all those scenarios already trained, and then we could implement that in hardware, for example, and then the hardware would say the HVAC system to change the temperatures based on some scenarios, what the sensors pick up. So that is one idea we could do in a real time.
All right, thank you. I would like to know why there is a spike initially in plots for cabin comfort.
So yeah, as we decrease the sensation, maybe I can bring up that slide. So for example, yeah, when we look at here, so when we decrease the sensation, the comfort increases, right? And it reaches a point where it further drops because we are still decreasing the sensation. So that's why we see that spike here. And then later when we maintain the sensation close to the neutral state, then we see that the comfort also has the constant flat line, more or less. And this spike can be because of the transient effect as well. So this is a transient simulation, and based on the flow of the air and the temperature, you get those transient effects, and the spike is purely the result of the transient effect, actually.
All right, thank you. What's the accuracy of the data with physical testing correlation?
So for this type of study, we have not done like a validation or done a physical test. So here we show the approach, like how we can do this type of study and how we can use the comfort and sensation of a human to design a controller and so as to save the energy. But yeah, but with that being said, yeah, the validation can also be done, but on the comfort and sensation of the human, we already have done quite few validations, so on our model. So yeah, we believe that this model will predict the nice results or results which we needed.
Yeah, and I can address that question from the 1D side. So so typically our components are physics-based components. They're not just data underneath. So they have physical information, geometry information, and physics-based correlations. So what we typically do when we implement, say, a refrigerant system model is we of course put in all the geometric parameters that our model requires, and then we will typically do a calibration process, component by component, if that data is available, to ensure that we dial in the correlations to match specific parts. I'd say in general, we're always aiming to get, say, between 5 and 10% accuracy on the component level with the calibrations that we do, and that's typically something we can achieve over the operating range of the components. And obviously, you put all those components together in the system, and if you have system data, you can tune at that point too. But you would tend to get sort of that same range at the system level, assuming you've done a good job at the component level. That's where we that's where we aim to get on the 1D side, and can typically achieve that.
All right, thank you. How do you account for external flow, including natural convection of environment and air gap between the battery and floor pan?
Okay, that's a good question. So yeah, we do have a wind convection model. So we have the weather file included in here, and when we have the wind information, so that is already included in this simulation. So we assume that car is moving at some speed, like as we gave that input drive cycle. So with that kind of scenario, we have averaged that the car moves in certain speed, and we have the wind convection on outside of the vehicle. And regarding the gap between the battery and the vehicle, so that is not modeled here. So the external airflow, like that is modeled from the weather file. It's not coming from CFD, but when it is needed or when it is crucial to have that air gap, and what would that bring to the battery cooling, yeah, we could very well do that simulation as well. But yeah, this will of course increase the overall turnaround time. Yeah, that is very well possible, but in this case we have just taken the wind from the weather file and modeled the convection, but not as a full-blown CFD.
All right, thank you. Are we limited to FMU integration, or are you able to bring direct coupling of 1D tools into TAITherm?
So the FMU is the typical standard we use to couple different 1D systems. Yeah, that's our main approach here. So that's how the TAITherm can interact. But if the customer has 1D system itself, we can also couple certain parts. I think just if the 1D tool supports some kind of input like IO functions, like reading some CSV files or data files, that can be done using TAITherm as well.
Okay, thank you. How does TAITherm in two-way coupling with Modelon directly or through FMU?
In this example, what we shown here is with FMU. So basically the 1D system is packaged as a FMU, like John mentioned, and then we use the FMI standards to interface the 1D system tool with other CA tools.
All right. Can you also look at winter heat up scenarios?
Yeah, that is still possible. Like John mentioned, in the different types of HVAC architecture, yeah, we could include like a heat pump from the 1D system side, and then also on TAITherm side, we could add like some radiant panels, heated steam, neck warmers, etc. So in this case, yeah, we could leverage 1D as well as 3D to do the heat up scenario as well.
Yeah, and typically in those scenarios as well, you would get not just the refrigerant system, but also potentially some different heaters, whether those be on the air side or the coolant side, that would be part of the mix here, and being able to heat under different environmental conditions. So yeah, definitely something that we do fairly routinely on the 1D side.
All right, well, looks like that'll do it for questions. So thank you, Vishnu. Thank you, John. That will complete today's webinar. We appreciate everyone for attending. You will all receive a follow-up email later today containing links to download the presentation slides as well as watch the recorded webinar session. Again, thank you everyone and have a nice day.
Yeah, thank you everyone. Thanks for attending.
Thank you.